Hello learners, welcome to the course Statistical Methods for Economics, Bivariate Random Variable, Discrete. In this session, we will discuss the concepts related to bivariate random variable, joint probability distribution for a discrete random variable, distribution function of a bivariate discrete random variable, importance of a bivariate random variable in economics. In the previous module, we have discussed techniques of solving the problems of normal distribution using the distribution function. Also, the concept of fitting of normal distribution with an example and generating random samples from normal distribution with the help of an example has been discussed. So far, we have understood only one random variable on sample space, whereas it is also possible to define more than two random variables on the sample space. For example, if we are interested in recording the income and expenses of the people in certain organization, then to describe such experiments, mathematically we need to understand the study of two random variables. A bivariate discrete random variable is a statistical concept that involves two related random variables that can take on the countable number of possible values. This means that each of the two variables can only take on certain values, and these values are finite or infinite but countable. Now, let us define a two-dimensional random variable. Let x and y be two random variables defined on the sample space S. Then, the function x, y that assigns a point in R square is called a two-dimensional random variable. A two-dimensional random variable is said to be discrete if it takes at most a countable number of points in R square. Two random variables x and y are said to be jointly distributed if they are defined on the same probability space. The sample point consists of two tuples. If the joint probability function is denoted by probability xy of x, y, then probability of a certain event E is given by probability xy of x, y is equal to probability of x, y in E. Now, let us define a joint probability mass function. If x, y is a two-dimensional discrete random variable, then the joint discrete function of x, y is called the joint probability mass function of x, y denoted by p of x, y. It is defined as p of x, y is equal to probability of x is equal to xi, y is equal to yi for all xi, yi of x, y 0 otherwise. For a discrete distribution, the probabilities can be tabulated as below. For any bivariate function denoted by p of x, y to be a probability mass function, the following conditions is to be satisfied. Firstly, p of x, y should be a non-negative function for all x, y in the range of x and y. Secondly, the total probability of all possible values of x and y should be equal to 1. That is, summation I is equal to 1 to n, summation I is equal to 1 to m, p of xi, yi is equal to 1. Now, let us look into the concept of bivariate distribution function. The distribution function of the two-dimensional random variable x, y is a real valued function f defined for all real x and y by the relation f(xy) of x, y is equal to probability of x less than or equal to x, y less than or equal to y. The bivariate distribution function is typically denoted by f of x, y and satisfies the following properties. F of x, y is non-negative for all x, y in the range of x and y. F of x, y is a non-decreasing function with respect to both x and y. For the real numbers a1, b1, a2 and b2, probability of a1 less than x less than or equal to b1, a2 less than y less than or equal to b2 is equal to fxy of b1, b2 plus fxy of a1, a2 minus fxy of a1, b2 minus fxy of b1, a2. If f of xy is a distribution function of two-dimensional random variable x, y, then f of minus infinity is equal to limit xy tends to minus infinity f of xy is equal to 0 and f of infinity is equal to limit xy tends to infinity f of xy is equal to 1. Now, we shall look into the problem solving of a bivariate random variable. Determine whether the following probability distribution is a PMF or not. For any joint function to be a probability mass function, the two conditions that are to be satisfied are P of x, y should be non-negative function for all x, y in the range of x and y. The total probability of all possible values of x and y should be equal to 1. In the given problem, observe that the values of x is 1, 2 and values of y is 1, 2. The table gives the probability values as probability of x is equal to 1, y is equal to 1 is 0.1, which is greater than 0. Probability of x is equal to 1, y is equal to 2 is 0.3, which is greater than 0. Probability of x is equal to 2 and y is equal to 1 is 0.4, which is greater than 0. Probability of x is equal to 2 and y is equal to 2 is minus 0.2, which is not a non-negative function. Hence, the first condition is not satisfied. Also, adding all the probability values, that is 0.1 plus 0.3 plus 0.4 minus 0.2, the sum is 0.6. Whereas, for a function to be a probability mass function, the sum of the probabilities should be equal to 1. As the conditions for a joint function to be a probability mass function is not satisfied, the given distribution is not a probability distribution. Check whether the given distribution is a joint distribution or not. For any joint function to be a probability mass function, the two conditions that are to be satisfied are P of x, y should be a non-negative function for all x, y in the range of x and y. The total probability of all possible values of x and y should be equal to 1. In the given problem, observe that the values of x is 1, 2, 3 and values of y is 10, 20. The table gives the probability values as probability of x is equal to 1, y is equal to 10 is 0.2, which is greater than 0. Probability of x is equal to 1, y is equal to 20 is 0.1, which is greater than 0. Probability of x is equal to 2 and y is equal to 10 is 0.3, which is greater than 0. Probability of x is equal to 2 and y is equal to 20 is 0.3, which is greater than 0. Probability of x is equal to 3 and y is equal to 10 is 0.1, which is greater than 0. Probability of x is equal to 3 and y is equal to 20 is 0.1, which is greater than 0. Hence, the first condition is satisfied. In order to verify the second condition, add all probability values, that is 0.2 plus 0.1 plus 0.3 plus 0.3 plus 0.1 plus 0.1. The sum is 1.1. Whereas, for a function to be a probability mass function, the sum of the probabilities should be equal to 1. As this condition for a joint function to be a probability mass function is not satisfied, the given distribution is not a probability distribution. Determine whether the following probability distribution is a PMF or not. For any joint function to be a probability mass function, the two conditions that are to be satisfied are P of x, y should be non-negative function for all x, y in the range of x and y. The total probability of all possible values of x and y should be equal to 1. In the given problem, observe that the values of x is 0, 1 and the values of y is 0, 1. The table gives the probability values as probability of x is equal to 0, y is equal to 0 is 0.2, which is greater than 0. Probability of x is equal to 0, y is equal to 1 is 0.3, which is greater than 0. Probability of x is equal to 1 and y is equal to 0 is 0.1, which is greater than 0. Probability of x is equal to 1 and y is equal to 0 is 0.4, which is greater than 0. Hence, the first condition is satisfied. Now, adding all the probability values, that is 0.2 plus 0.3 plus 0.1 plus 0.4, the sum is equal to 1, which implies that the second condition for the function to be a probability mass function is satisfied. As both the conditions are satisfied, we can say that the given probability function is a joint PMF of the random variables x and y. The joint PMF of two discrete random variables x and y as given below. Find probability of x is equal to 2, y is equal to 1. From the given information, we observe that all the values of the function are non-negative and then the sum of all the values is equal to 1. Hence, the given function is a probability mass function. From the table we have, for x is equal to 2 and y is equal to 1, the cell value is 0.3. Hence, the joint probability of x is equal to 2 and y is equal to 1 is 0.3. A box contains 5 red balls and 3 blue balls. 2 balls are selected at random without replacement. Write the joint probability distribution table and hence determine the probability of selecting one red and one blue ball. Let us define x as number of red balls selected and y as number of blue balls selected. From the given information, there are 5 red balls and 3 blue balls. So, the total number of balls is 8. Out of these 8 balls, 2 balls are selected without replacement, and the selection can happen in the following ways: 0 red balls and 2 blue balls, which implies probability of x is equal to 0 and y is equal to 2 is equal to 5c0 into 3c2 divided by 8c2, which is equal to 3 by 28. 1 red ball and 1 blue ball, which implies probability of x is equal to 1 and y is equal to 1 is equal to 5c1 into 3c1 divided by 8c2, which is equal to 15 by 28. 2 red balls and 0 blue balls, which implies probability of x is equal to 2 and y is equal to 0 is equal to 5c2 into 3c0 divided by 8c2, which is equal to 10 by 28. As only 2 balls are selected, all the other combination of x and y values would be not possible. Hence, the probability of all other combinations is 0. The tabular representation of the probability distribution is as follows. Now, from the table, we observe that the joint probability of getting one red and one blue ball is probability of x is equal to 1, y is equal to 1 is equal to 15 by 28. 2 coins are tossed at same time, one fair and one biased. The biased coin has a probability of 0.8 of coming up heads, while the fair coin has a probability of 0.5 of coming up heads. Assume x be the number of heads on the fair coin and y as the number of heads on the biased coin. For the possible values of x and y, construct the joint probability mass function and hence find the probability of getting exactly one head. Let x be the number of heads on the fair coin and y be the number of heads on the biased. Hence, the possible values of x and y are 0 and 1. As the given events are independent, we have probability of x is equal to x, y is equal to y is equal to probability of x is equal to x into probability of y is equal to y. The joint probability distribution for x and y is probability of x is equal to 0, y is equal to 0 is equal to probability of x is equal to 0 into probability of y is equal to 0, which is equal to 0.5 into 0.2, which is equal to 0.1. probability of x is equal to 0, y is equal to 1 is equal to probability of x is equal to 0 into probability of y is equal to 1, which is equal to 0.5 into 0.8, which is equal to 0.4. Probability of x is equal to 1, y is equal to 0 is equal to probability of x is equal to 1 into probability of y is equal to 0, which is equal to 0.5 into 0.2, which is equal to 0.1. Probability of x is equal to 1, y is equal to 1 is equal to probability of x is equal to 1 into probability of y is equal to 1, which is equal to 0.5 into 0.8, which is equal to 0.4. The tabular representation of the probability distribution is as follows. Now, from the table, we observe that the joint probability of getting exactly one head is probability of x is equal to 1, y is equal to 0 plus probability of x is equal to 0, y is equal to 1, which is equal to 0.4 plus 0.4 is equal to 0.8. Now, we shall look into some applications of bivariate discrete random variable. Demand and supply analysis. Bivariate discrete random variables can be used to model the joint distribution of demand and supply in a market. This can help economists understand the relationship between the two variables and how changes in one variable affect the other. Investment analysis. Bivariate discrete random variables can be used to model the joint distribution of returns for two different assets. This can help investors understand the diversification benefits of holding multiple assets and how the returns of one asset affect the returns of the other. Risk management. Bivariate discrete random variables can be used to model the joint distribution of two different risks. This can help risk managers understand the relationship between different types of risks and how they can be managed. Game theory. Bivariate discrete random variables can be used to model the joint distribution of two-player strategies and payoffs in a game. This can help economists analyze different types of games and determine the optimal strategies for each player. Industrial organization. Bivariate discrete random variable can be used to model the joint distribution of two firms' market shares in a market. This can help economists understand the competitive dynamics of a market and how changes in one firm's market share affect the other firm's market share. Summarization. In this module, we have understood the concept of a bivariate random variable, what is the probability mass function of a bivariate random variable, its distribution function, and then solved some problems on these concepts. Finally, try to understand the applications of the bivariate distribution in various domains of economics. Thank you.